I'm Dianli Liu from Tinty University, and it's my great pleasure to give a talk on the topic small data analytics for enhanced situational awareness of the smart grid. And in my talk, I would like to share three things. First of all, I would like to introduce a new distributed paradigm of power grid inspired by the internet. And then I will give the basic idea about the situational, especially give the relationship between the situational awareness and also the data. And finally, I will give some practical ongoing research cases on the small data analytics for enhanced situational. I believe everybody is really familiar with these pictures. And since the global climate change is really urgent and large due to the greenhouse gases from the human burning fossil is already taking place. So the left picture shows the leaders from around the world collectively agreed in 2015 in Paris that human behavior induced climate change is a threat to all humanity and actions must commence immediately to limit the temperature increase in this century to 2 degrees while pursuing means to limit the increase to 1.5 degree before the window of opportunity close around 2030. So the decarbonization of electricity, both switching from fossil fuel to renewable and other non-fossil sources, coupled with the increased electrification of other sectors of the economy, is considered to be an effective pathway to the sustainable development. So a new era of electricity is coming. Here are some numbers about the supply side and the demand side uh, numbers. And we can see that actually from the supply side, the renewable energy has rapidly developed. And in 2021, more than 315 gigawatt of new renewable power generation capacity was installed, and renewable electricity accounts for 28.3% of the global electricity production, and the wind and power accounts more percentage. And for the demand side, there's a uh, representative part that's about the transportation sector, and we know more and more electric vehicles have progressed rapidly in the last couple of years, and the IEA forecast that in the new policies scenario, the number of EV on the road reaches 125 million by 2030. So if more renewable energy and EV integrated into our power grid, and that means both supply side and also the demand side will be intermittent and variable and stochastic. And that's a really big, huge challenge to the current power grid operation. And since we know in the past that the basic idea of the power grid to do the operation, we do the generation control to follow the load. And now both supply side and demand side, the characteristic really change a lot. And that means we really change the basic idea about our power grid and to integrate more sources that the sustainable development requires. So a smarter grid is urgently needed to achieve the vision. Hundreds of millions of people will produce their own energy from renewables, store it locally in batteries in their homes, offices, and factories, then they share it with others through the grid. So we can find that actually the future version is really similar with the internet, that we share the information and we produce our information and share the information through the internet. So a new distributed paradigm inspired by the internet is proposed by our team. As the left pictures, so we should firstly to know why the internet is smart. And the left picture shows the basic paradigm operated by the internet. And we can see that the internet is a network of subnetworks structured in a hierarchical manner with a number of tiers. At the top is the global internet, followed by several tiers, including the network service provider backbones and internet service provider backbones, and so forth. And then at the local area network or users at the bottom. So on the right, I give a picture to show a really simple example. And that means if A want to send an email to the user B, and both these users are located in different places. Maybe the A is in Tianjin located and B is in the USA. So the user's A's computer is connected to local area network and her email is served by the internet service provider backbones in China. So the email may have to hop through a few intermediate points in the internet service backbone network to reach a network service provider, both of a large international network of the global internet are similar for B. And but user A and user B may not belong to the same network service provider network, and the email will have to exchange through a network accessing point between the two network service provider. So the point-to-point path along which the emails travels can be traced from the A's computer in Tianjin to a local area network and then internet service provider, and then the network service provider, and another SPSP and local area network, and finally to the B's computer in USA. So we can clearly to see that actually the email is routed in the through a numbers of routers, and the information exchange between the routers is governed by a really famous and well-known TCP/IP stack, and which includes layered communication protocol specification. And in the middle, we show the TCP/IP stack, and we can see that the upper layer uses functions available in the next layer and instructs the next layer what to do. The instruction is coded as a header added to the front of the message, and each layer adds a header on the way down. So this process reverse on the receiving end and layering allow the decomposition of a simple and compliance task into a simpler, clear, and coordinating subtext. So the internet is made to work flawlessly and efficiently by design of the network structure and layered architecture of the operational protocols. So inspired by the internet's intelligence, a new operating paradigm of the grid with distributed intelligence and responsibility sharing is developed. And we can design the whole power grid structure and into hierarchical clusters. We call it connected subgrid of the grid, consisting of cluster of prosumers with the intelligence to manage and control at a night power balance a cluster. And two clusters cannot partially overlap because if they do, none of them can manage their own net power balance. Therefore, two clusters are neither non-overlapping or one is completely contained inside the other, just like the internet operate. So a cluster may contain many clusters or none at all. So a cluster that it is a part of a larger cluster may contain several clusters. So this is the global structure about this natural hierarchical of clusters arranged in tiers. At top of the hierarchy is a whole interconnected grid, and one tier below could be a power authority or a company with its own EMS operated as a control area in the interconnection. So the bottom tier could be a smart home. And just like the internet have the intelligence, a cluster must have the intelligence to manage and control its net power balance. And energy management system of a cluster considering of all necessary hardware and software to manage and control its net power balance is equal to a router in the internet, and it can be called the energy router. So just like the TCP/IP rules and the three layers, you can see we show a really simple example here, and we can also design three layers, namely market layer, schedule layer, and balancing layer for each cluster is proposed. And the users agreed that the prosumers integrate with the electricity market to share or trade electricity. The transaction must be scheduled and realized physically on the grid, and the net power of the cluster must be balanced at all times. And here's a simple example from A to B in the hierarchical of clusters, just like the TCP/IP protocols are designed by the internet. And more details about this work can be found in our paper published in the journal Engineering. So the reason why I gave the idea that is we can see if we want to integrate more and more renewable resources and distributed EV and the other sources are located in the user's site, and that means the whole grid architecture is the most important. And under this design, each cluster must know how themselves integrate with the other clusters. And meanwhile, and the cluster must manage their own power balance. So the situational awareness is really an important part for each cluster. And just like what it played the critical role in the past few years in our EMS. And about the situational awareness, actually it is defined as the perception of the elements in an environment within a volume of time and space, the comprehension of their meaning and the projection of their state in the near future. And what's simple to say, I just like doing the medical examination and then providing the report for a further decision. And it helps the operator aware what is happening and future trend and to take effective measures. And during different layers, actually the situational awareness provide many information for the operators. So we can see the information from the table in the perception layer. And actually, we will provide the generation data, transmission plant outage, load forecast, transaction schedules, and plant and actual reserves, and the switch breaker status, information on neighboring systems, and identification of limit violations. And then when based on the perception layer, we will do a more comprehension about the operating status, and we will know the deviation between the actual and planned status. Especially, we will know the distance between the operating state and also the boundary. And meanwhile, we will further know the status of the equipment, the system capability and vulnerabilities and available actions. And then in the final layer, and we will aware the future system state, and we will know before the timely operation comes. So we will also would like to know the time for actions implementation between the timely operation comes. So we can see that actually through the situational awareness, and we will know what the power grid, the operating status, and help us aware the current status, and also to do the predicted actions to avoid some serious accidents. So I would like to give another loop to understand the basic idea deeply. And actually, we can see actually the the power system is a really actual physical system, right? And so that means there is always the actual power system state. And what we want to do is that we want to know the real actual power system state, and through the framework architecture established in the past few years. So actually, during this whole architecture, there's a really loop existed. And actually, we installed some ICT infrastructure. And that means we install the meters and the control devices and also the other on-site equipment around the really important elements in the power grid. And then we will collect some information and data. Actually, after this process, we will get the presented power system state. And actually, the situational awareness, they do the analysis based on this state. And then after doing the situational awareness analysis, actually we will give the information to the operator. And actually the operator, different operators see the same information, but they will establish different picture about the power state in their minds. So that means after the operator's situational awareness, there will be the perceived power system state. And actually the operators do the decision making based on this state. And then we translate the command control signal and again through the ICT infrastructure. And that means we send the control signals and our actions and to the on-site equipment to control the real power grid, and then the actions will implementation, and then it will affect the actual power system state. So through the loop, and we can see that actually the information and the data collected from the actual power system state side is a really critical role to help us establish a really accurate perceived power system state, which is we will like more closer to the actual state is more better, right? So the data and the information is really the basic part to do the accurate, effective situational awareness. And meanwhile, the situational awareness is more and more critical to each cluster operated in the hierarchical of the architecture of the future grid. And here I give some overview about the data situation. Actually, on the left picture, and we can see that with the development of the advanced measurement infrastructure and also the equipments, more and more data will be collected. And that means we are really entering a data-intensive area, whereas a vast volume of data is collected. And if we focus on the detail of the data, we will see actually we got multi-scale temporal and spatial data size. And actually it really contains comprehensive information. So the left picture will show if we take advantage, take use of the single data value, and it can help us do better system operation, especially situational awareness and fault diagnosis, interruption recovery, prediction, distributed power dispatch, and also electricity charges. And meanwhile, actually, if we can integrate the different source of data and we can extract more data value from the historical analysis value, we can do better business integration, long-term operation, deep analysis, and also we can do a size management phase identification based on the AMI. So the conclusion that the data really have a more and more very good value. But its big data is good, and I believe many of you can see the reports and the papers, and also do some communication in the conference. And we can always see the title, the big data analytics for Balabala, right? But we can clearly know that a huge amount of data requires better ICT infrastructure and higher cost to collect and store, right? And meanwhile, in some cases, and no matter how many meters we installed, we still face a small data situation. Here, I give three kinds of example. And for the supply side, particularly for the wind and solar, and we all know that the wind and solar is probabilistic, right? And actually, we all know that more and more extreme weather happens. And actually, we lack the extreme weather samples about the wind and also the solar power. So the video and also the picture show that that's really happened in China about the cold wave in last year. And actually, we communicate with the biggest wind farm in the Jibei of China. Actually, we have really good data quality, and that means we collect each wind generators data, and we really have a good data quality. And meanwhile, we do the accurate prediction about the wind power. However, under the cold wave happened in that year, we do not do the good forecast, and it really affect the real operation of the whole power system. And for the grid, actually, I take part in another IEEE working group as the host introduced, and also under the BDA subcommittee. And we do the research and communicate in the scope that we introduce the data-driven methods in the dynamic security assessment. And we all know that actually, especially from the China power grid, we has already do the design about the whole power system. And that means we make sure the power grid can can stand the n minus one and n minus two and even n minus three quantities. Yes. However, if we want to know the real secure boundary about the whole system, actually we really need the unstable samples, operating points samples, right? So that means we got a lot of data about what the system is secure, but insecure data samples we really lack of. And meanwhile, actually, for the distribution network, especially under the future grid change, distribution network becomes more and more smart. And that means we also install more and more meters and also do the similar thing like the transmission side do. So it is more complex and changeable, but with lower measurement redundancy. So it is difficult to directly obtain its topology structure. Meanwhile, distribution network topology tends to be mesh configuration, and the frequency of topology changes will continuously increase with increasing penetration rate of the distributed energy resources. So that means we also lack of enough data. And meanwhile, for the load side, actually, we know the complete load data is really crucial to advanced load data to support the the demand response, right? And however, due to the hardware aging, hash measurement requirement, and actually large percentage of data missing and continuous data missing is really existing in the practical projects. Actually, we do the verification on the actual industrial load data size, and it showed that different cases has the different percentage of the missing data. And here is a really serious one. We really have the good quality of the meter system, and that means each equipment have has itself meter. However, the average data missing ratio is 1750%. So combine these two big background, and that means the big data require high cost to about the ICT infrastructure and also the operating cost about the data. And meanwhile, actually, there really exist the many small data practical situation. So I ask myself a really important question: and big data is good or smart data is good? And from the data store and operation cost side, the small data is better. And meanwhile, we show the cases that in the real operational cases and many small data scenarios really exist, and then it's not the small scenarios. So this inspired our team to do the small data analytics for the enhanced situational awareness. And that means if we can do the same thing, only use the small data, it will save the cost about the ICT infrastructure and also the data store and operation in the later stage. So, and before I introduce some practical research, I would like to give an overview about the data analytics application in the power system. Actually, there's the milestone around 2000, and before that, we introduced the statistical learning methods that like the decision trees, SVM, and natural networks in our area. And actually after that, and actually we really enter the era of deep learning and big data analytics. And we are very familiar with the CNN, RN, and it really have achieved greater success in fields like image recognition, speech recognition, natural language processing, and the classification of the data methods application in the power system analysis. There are some typical areas. For example, we do the regression problems solved based on the deep learning, and the typical problems including the load, renewable energy, and other forecasting problems. And we also do the clarification problems based on the deep learning, such as the power grid equipment fault diagnosis and stability assessment and the other typical problems. And we also introduce the decision-making problem based on the reinforcement learning, such as the voltage control strategy, charging strategy, and so on. And especially in the recent years, and we more and more big data methods and also the AI methods introduced in our area. And actually, we have the LSTM used for the load forecasting, transformer used for load forecasting, and also the PNN in power system, and also the large-scale time series models is very hot in this year. And we can clearly know that the application of the data-driven methods in power system analysis is somewhat lagging behind the development of the method themselves, and the current lagging application is gradually shortening since our subcommittee really play a really critical role to push forward this area. And that means more and more researchers in power system really focus on the interdisciplinary research, combine the big data data analytics methods and AI in the power system. And actually, in recent years, the application of data methods has shifted from focusing on the accuracy of fitting a linear relationship to describing uncertainties in physical quantities, enhancing the interpretability of models, improving the generalizability of the models, and integrating with traditional physical computation models. And so, based on the overview, actually, I just focus on the small data scenarios I introduced. I just introduced. I would like to introduce three kinds of work. Especially, I will especially introduce the idea and in the small data analytics for the enhanced situational awareness, and they are adaptive wind power prediction under extreme weather conditions. And I will also introduce the operational situational assessment and the small data size, and also the load image impeding research works. So about the wind forecast, actually, we are really familiar with this topic. And traditional methods mainly focus on the point forecasting, just like the left picture shows, and which calculate the expected value of the wind power output in the future. However, due to the inherent uncertainties and random of the wind resources, invariabilities variance may appear. And on the left picture, more and more attention are paid to the probabilistic forecasting, which is better quantifies uncertainties of wind power output in form of quantized and prediction intervals. Density functions has received much more attention in power system. So we do the probabilistic wind forecast. However, here the problem, and we all know that under complex and variable weather conditions, and we actually we have many data analytics and AI models introduced in this area, and the latter picture gave a review about the methods application in the wind forecast, especially the probabilistic wind forecast. And we can find that actually most of the models they are trained based on the historical scenario with inherent network structure and parameters. And that means, and once we got the network structure and parameters, and then it is designed to do the work to do the wind power prediction. And however, the wind situation changed timely, and under complex and variable weather conditions, we use the fixed network structure and parameters to do the future wind forecast. It has the limitation, and we do the compression analysis as really is low adaptability and generalization capability for future scenarios, especially in the right the down pictures, and we show the cold wave extreme weather wind situation. Actually, especially under the extreme weather conditions, the fixed network structure and parameters will has a bigger limitation. So the idea is that we are bringing the transfer learning and to do the adaptive probabilistic wind power prediction. And actually, the idea is that we want to do we want to we want to how to say like the model do not have the limitation about the fixed model and parameters. So we bring in the model-based transfer learning to optimize the network structure and improve the nonlinear fitting ability of the original network. Actually, we do the work based on the ERM is a really familiar model extreme learning machine. So the model-based transfer learning is used to construct the multi-layer extreme learning machine. And also, meanwhile, the output mapping factors of the multi-layer extreme learning machine are further optimized through the particle swarm optimization with the objective of minimizing of the quantile evaluation index. And about the idea, the second part is that we introduce and bring in the future transfer learning to mine the intrinsic feature representation from the time series wind power output. And then the network parameters are effectively updated to improve the adaptive of the model parameters. So the joint distribution adaptation is utilized to explore historical temporal variation characteristic and update widths of the multi-layer extreme learning machine to accommodate variable and wind power output. So the right picture gave the framework of the proposed method. And in the first part, the multi-layer extreme learning machine is constructed through the model-based transfer learning, and featuring inputs are historical wind power output, while outputs are quantities of wind power output to be forecast. And then the output mapping factors of the multi-layer extreme learning are further optimized through the particle swarm optimization method with the objective of minimizing quantity evaluation indexes to enhance the quantile regression results. And finally, the weights of the multi-layer extreme learning are updated by the GDA from the feature-based transfer learning, take the weights and the historical moments as training data sets to adapt to variable wind power output. Actually, this is the key three steps as I introduced. We construct the multi-layer extreme learning, and we do the parameter optimization. And finally, we update the weights based on the feature transfer learning. And more details can also found in my papers. And here are some test results. And actually, we cooperate with the biggest wind farm in China, and that is the Jibei wind farm. And the data quality is very good. And we do the test, use the data resolution for 15 minutes. And here the model optimization effect based on the transfer learning. And this is the three kinds of results to show the three steps results. And from the left pictures, we can see that using the model transfer method, the quantile regression results decreased to 75% to 90% of the initial value during the transfer process. And in the middle picture, we can see that after optimizing the multi-layer extreme learning machine using particle swarm optimization method, the evaluation indicators can be optimized by 10% to 33%. And finally, there's a significance in the width of the multi-layer extreme learning machine for adapting to wind power output characteristics at different time periods. And the proposed method can improve the model's parameter self-adaptability. So the right picture shows the updated weights about the multi-layer extreme learning machine. We can clearly find that we really need to update our model and parameters once the time passed by. Yeah, and here are the results to show the real calculation results about the wind power probabilistic prediction. And actually, the left picture show the predict results, especially about the probabilistic forecast results. and we can see that we can accurately uh, do the forecast a task, and especially and during the results, actually we give the probabilistic uh, results, and actually the actual wind power output, and that's the yellow line, and we can see that all the actual wind power output located in the results what we obtained. And meanwhile, we can do the accurate and reliable quantity prediction results. It can be obtained for peak and value nodes. Now, meanwhile, we also do the comparison with our method and also with the other classic methods, including the BPN, NCN, LSTM, and also the extreme learning machine. And we can see that actually the reliability metrics and skills growth metrics are better than the other methods. And however, we once we got actually this method proposed before the cold wave event happens, and once this cold wave happens, and we got the data and we test in the transfer learning, I think we found that actually the results is still good. However, it's not to however, it's not the our expected results. So we can see that actually in practice, abandoned training samples are playing critical role in the effective training process of existing forecasting models. So considering extreme events with low probability poverty, the scarcity of relevant features measurement cannot meet the numbers of training samples required, which severely limits the effective training process of the model, making the accuracy of existing forecasting model significantly under extreme events and posing great challenges to generalization capability. So the idea is that we introduce the reinforcement learning to realize effective data enhancement and optimize model parameters adaptively. The general framework is given here, and actually there are three key parts. We evaluation index for the mutation characteristic and extreme events is constructed. An error evaluation model is then established with quantity regression loss function introduced, and the index takes as the benchmark. On this basis, the deterministic strategy gradients based on quantity fitting model is proposed with the aim of minimizing the long-term error feedback, where experience replay pool is utilized to establish effective training samples under small data size by extracting key historical transition and model parameters are updated through the small bench learning. Anyway, we do the test case on the practical situation, especially based on the real cold wave weather data. And we can see that at nodes with significant sudden changes in output, the quantifiers obtained by the proposed methods can effectively include the actual wind power output, even in extreme scenarios. We also do the comparison analysis actually in the conventional, and that means not the extreme weather conditions. The reinforcement learning is slightly better than, but close to transfer learning, but both indicators are far lower than the other methods. But in the extreme scenarios, the reinforcement learning targeting extreme scenarios can achieve better probability prediction results. So this the first kind of work. And the second cancer is about work is about the load image empathing. Actually, under compliance and variable actually, we all know we have the missing data, and even we have the high percentage of the missing data. So joining on the ideas from the image embedding, so we formulate the load missing data recovery problem as load image embedding, and the improved unite is proposed to restore the load image. So the idea is that firstly, the one-dimensional load data is constructed into two-dimensional load image. Additionally, missing data presents irregular black holes on the load image, and then the improved unite, which introduce the residue network and convolutional block attention module is proposed to restore the input load image. So we do the test case in the real industrial park data. And actually, we also propose a new index. We call it mean observed error. And also the structural similarity are utilized to evaluate data recovery occurrency and load pattern recovery similarity respectively. So entry, we set different missing ratios from 25 percentage, 50 percentage, 75 percentage, and even 85 percentage, and we train the proposed method riskily. And we can see it can be vividly see that there's little difference between the output load image and the original load image even under high missing ratio, and it is very find effective as a proposed method. And actually, we do the comparison. Actually, all the proposed methods can achieve the highest degree of load characteristic recovery similarity, but the small proposed methods can have robotics for different missing cases. Actually, this is ongoing work, and currently we are designing a really new, but the idea is similar. And the three candle is about the topology and parameter joint estimation of distribution network based on the PCA. And actually, time varying characteristic of distributed networks makes the measurement data of intelligent instrument in the same state not enough, which cannot satisfy the required amount of data in existing topology and identification. So that means actually we have the so actually the key problem is that actually it is the multi-collinearity bring challenges to topology identification. That means we unable to identify loop networks and the measurement data in the same state is limited. And that means we only got the small data size. And here's a review about the current research status and problems. And so we do the work based on the partial correlation analysis. Actually, and we can see the left picture where the color in the square represents the correlation coefficient among nodes. And that means the closer the color is to yellow, the higher the correlation between the two nodes, as well as higher likelihood that the nodes are connected. So the PCA efficiently remove the effect of the collinearity and reveal the connection between two considered nodes. The partial correlation coefficient between neighboring nodes is close to 1, and between non-neighboring nodes is close to 0. So considering the PCA can reveal the intrinsic correlation of two variables by eliminating of the influence of the other variables, we propose the PCA-based topology identification method. Here's a basic framework. Actually, we division the big problem into 3 steps problems. And firstly, the maximum spanning tree of network is generated through the priming method. Then the loop of the network are identified by taking tree neighbors as controlling variables in PCA. And finally, a new topology verification based on PCA is developed to correct the wrong connection caused by the multicollinearity. And we do the case study on the IEEE 33 node system and IEEE 123 node system, and also the real 49 node distribution network in China. And here are the results of the topology generation process and calculation results of the different example systems. So we can clearly see that the identification of the loop network is realized and the application scope of the existing method is enhanced, and the error caused by the collinearity is corrected, and the accuracy of the topic recognition is improved. And meanwhile, we do the test in the system, including the distributed energy resources, and we can also find that the method is suitable for the ratio Marshall or even the distribution networks, including the distributed energy resources of different scales, and has strong robotics. And actually, we have the vivid map and can help us to show the status of the line. It has a really huge application scope. And based on this work, actually, as I introduced just now, actually we do not have the enough data size to do the joint estimation about the topology and the line parameter. So the key idea is that actually we have the really enough physical knowledge about the pop system. So if we take use of the good physical knowledge, it can help us reduce the measurement data required for the data-driven methods. So we propose this method. So this is the basic framework of the proposed method. So based on the spatial characteristic of the distribution network and partial correlation analysis based on neighbor node selecting method is designed, and the initial topology and the small data size was robustly identified with all criteria, and combined with the linear power flow equation, the initial value of the line parameters and the phase angle estimated based on the linear regression. And furthermore, the initial topology line parameters and the initial phase angle are optimized based on the Newton method with the decoupled line power flow model. So details can be found in the paper, and we also do the same test case studies, and the results show that the proposed method can accurately estimate the topology and line parameters of the distribution network with different size and types using only dozens of measurement data. And compared with the existing method, the proposed method only needs small data size and has faster calculation speed with the same estimation accuracy. And we also do the sensitive test results, show that the proposed method is robust to noise and sampling resolution. And the final case, so the time is perfect. We have another around 5 to 10 minutes. And the final case is about the dynamic circuitry region boundary generation. And actually, we use model-based point-wise method, and that means we check whether the operating points satisfy the stability constraints by numerical calculation. And based on the method, the circuitry region methodology is developed. It provides the region in the decision space that all operating points inside can guarantee the stability. So here the definition, and the dynamic circuitry region boundary with the hyperplanes expression is called practical dynamic circuitry region. And that means given the topology, parameters, and fault, the practical dynamics curve region is unique and does not vary with the operating states. And its simple mathematical distribution made it very simple and feasible for application in a series of optimization problems considering secure constraints. And we can also do the three-dimensional visualization examples to help operators aware the current state, especially the distance between the operating state and also the boundary. And actually, many data-driven methods introduced in this area to identifying the boundary, right? And the key is lies in quickly obtaining enough critical points near the boundary. If we do the point-wise method, it might mean that we require a lot of computation to search point by point. And meanwhile, now here we can see the right picture, especially the lower one. Actually, we can generate many samples, and that means the secure samples and unsecure samples. However, we do not clearly know whether there's hole inside both sides. And meanwhile, we do not know whether the samples we generate is really located around the boundary. So that means the pure data-driven method about the reliability and the interpretability is not strong. So actually, about the security region methodology, we have already do many years research. Actually, we do the research on the typical differential topology characteristic about the boundary, and that means we has already proved that about the boundary, there's no nodes on the boundary and no holes inside. And that means the boundary only located in the area just in the middle between the secure area and also the unsecure area. So we propose a method based on the space division and also the WGN and GP. So the basic idea is that provided by the topology characteristic of the boundary with denseness, continuity, and compactness, space division, it can help us determine the critical operating area where the critical points are concentrated in. And if we can obtain this critical area immediately, it can help us compress the space to locate the critical points on the boundary. So the key idea is that we propose a Swiss division method to locate the critical area, and then if we have already compressed the searching space, and just in the really small space we can generate enough critical points data help us to generate the boundary as soon as possible. So this is a basic framework. And the left picture shows that actually we can divide the space into the secure area and secure area, and also the critical operating area help us to locate the critical points. And then we do the faster generation of the large number of critical points based on the learning of the data distribution of the small training site performance based on the WGN and GP. And then finally, we fit in the boundary based on the enough critical points. So here the test results, and we can see that if we introduce the space division method, it reduced calculation time by 17% compared to the only the relief method, and by 57% compared to the fitting method. And meanwhile, actually, the proposed method decreased the calculation time by 81% compared to the fitting method. And if we combine the space division and also the data-driven method, if we do the comparison, actually we combine these two together can save more time. And actually currently we're limiting the calculation time about the boundary within 6 minutes. So here the final conclusion. I would like to share 3 important ideas and also the conclusions. Learning from others' strengths can help refine our own. That means through the cases and also many results, especially under our subcommittee, we really need to introduce advanced data analytics and AI methods to help us to enhance the situational and the other problems we focus. And the second idea is that without taking small steps, there can be no journey over thousands of time. And that means we have classic models and methodologies. It remain enough time. We can see this conclusion from the many cases I just introduced, especially about the dynamic security region and also the top layer identification of the distribution network. Actually, we take use of the really good physical model knowledge and also the methodology. It can help us the data analytics methods playing a better role. And the final conclusion that holding firm to one's goals, and that means we should do the problem drive in charge of emotion in the theory, practical, and theory cycle. So I think that's the end of my talk and just 1 hour. So here's my information. I'm looking forward to more discussion and communication. So Professor Cui, my talk finished.
All right. Thank you, Professor Liu, for this wonderful talk. Yeah, Professor Liu covered from the novel smart grid infrastructure. Then she covered some topics such as topology identification, as well as generation forecasting. And yeah, I feel it's very interesting. Here, I have collected some questions from the audiences. And let me find the first one. Yes, the first one is related to how to use the limited data, such as only 1 year of PV generation data or whatever, or wind generation data, load data, TOU data. The question is how to use the reinforcement learning algorithm to train the agent more effectively to achieve the optimal energy management strategy of energy storage in order to achieve the lowest economic cost of the system and extend the service life of the battery storage.
Okay. Actually, that's a really detailed question about the reinforcement application in the wind forecast. Actually, actually, we have the papers. Actually, you can find the details. We designed the whole reinforcement learning, and actually, we divide the problem into different steps. Just as the audience asked the question, actually, we can find that he has already know the basic process, and he want to know the details about each process. I think the papers can give the detailed answers. I think, yeah.
Yeah. So we can refer to your paper, which maybe you provided to me through email, and also
yeah, no problem. Yeah.
Guys, we will upload it to your personal website created by HVPS. All right. So the next question, how can data privacy and security challenges be addressed in the application of small data analytics technology to enhance situational awareness of the smart grid? This question seems a big one.
Mm.
Yeah, so
Pardon?
privacy.
Yeah, the question
Yeah.
is that, yeah.
Yes, so how can data privacy and security challenges be addressed in the application of small data analytics technologies?
Mm-hmm. Actually, that's the final conclusion,
Mm,
and also the idea I shared. Actually,
yes.
we surely focus on the problem. Yeah, and that means we not the data-driven method is purely good, right? Yeah. So my idea is that you should focus what problem you want to solve under the big background, especially under the future great challenge, right? So
Mm,
every problem we can have the mathematical distribution. If the model based can solve, why we use the data driven? That's the first thing. And second thing, actually, we do the data driven and we have many methods, right? So we should do the mathematical analysis. If
mhm,
this problem, the data driven methods have the similar mathematical solved idea, it can might well, so we can introduce the data driven to the kind of problem. So I think that's my idea. The important thing is that we should clarify the problem very clearly from the mathematical level, and
mhm.
then decide the opportunity and also the challenge we bring in the data driven method in this area. Yeah.
Yeah, great. Yes, I also agree with it. So the next question is same from a student who is looking for some advices on research directions. Mm, he or she asked, do you think which research directions in the distribution network are facing the small data problem besides topology
Mhm,
identification? Do you
mhm,
have any suggestions for him or her?
mhm, mhm. Actually, from the data view about the distribution network, most of the problem are the small data side problem, right? But
Yes,
Professor Cui, the things
yes.
in the background I introduced about the distribution network, even in some really good demo projects in China and all over the world, the data quality is not enough, just like the big data, as big as we collected in the transmission side. And even in the future, more and more distributed energy resources will integrated in the distribution side. And that means the topology is changeable. And that means under the given topology, really limited data we can obtain in the current state. So that means for the distribution, we do the power flow analysis, we do the topology parameter estimation, and we do the filter optimization problem, right? I think all the problems can bring in the small data size idea in related problems. Yeah.
Okay, thank you. The next question. Small data is a type of data, but there may also be data quality issues. If there are issues with the data quality of small data, will it have a greater impact on the results? How to solve this problem?
Yeah, this question is very good. Actually, that's the key. We select the good methods. I mean the data-driven methods. So actually, in my talk, I gave some examples, and for the uh, load side, it's missing, just missing. So the problem is how we can recover, right? And but for the dynamic security boundary, the key is how can we obtain the samples we do not have. So different problems have different, uh, I think, a mathematical distribution. So we choose the matchable methods. So that's the first thing. And second thing about the question, how the small data size will affect the results. The goal is that we only use the small data size, but we do the same thing. And today's examples has already showed that if we choose and also design the good data-driven and even the hybrid data-driven method, we can only use the small data size and to get a really a good performance results. Yeah.
Yeah, also following this question, is it more difficult to handle the quality of small data compared to traditional methods of dealing with big data quality issues, such as prediction, supplementing missing data with average values, etc.? Yeah, I think you already answered some of this.
Yeah, similar question. Yeah, but I can add another comments. Actually, different data have different features. So the basic idea about many data-driven methods focus on how we can extract the features about the data, right? So different problems, we can also focus on different features we really interested in too. Yeah. So that means if we choose a matchable method, it really can help us recover the data with the same features the real data have. Yeah.